Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to your YouTube channel Chandan Physics. In this video, we are going to discuss VanderWaal's equation of state for real gases and comparison with experimental curves, means PV diagrams. Let's begin. For the ideal gas equation, if we take 1 mole of an ideal gas, PV is equal to RT. P with the pressure, V with the volume, R universal gas constant, T with the absolute temperature. In order to correct the error for neglecting the intermolecular force of attraction and the volume occupied by the molecules themselves, the scientist VanderWaal's introduced two correcting terms, one for pressure correction and another for volume correction. So, how the scientist VanderWaal approached two things: one, the intermolecular forces of attraction and another one, finite size of molecules. Due to the intermolecular forces of attraction that leads to the correction in pressure, and due to the finite size of molecules that leads to the correction in volume. Let we introduce how exactly the correction introduced. First, correction in pressure. For correction in pressure, we take what? VanderWaal's suggested that the correction term B should be subtracted from that of volume V in order to get the compressible ideal volume, so that the ideal volume in the equation should be V minus B. And the constant B, here the constant B is called the co-volume, that is known as the co-volume or excluded volume. Approximately, the co-volume is nearly 4 times the actual volume occupied by the molecules contained in that of gas. So, in this way volume is corrected as V minus B. Now, how? Okay, not that line, that is the this way, this is the volume indicator. Okay, that is for volume. Now, for pressure, taking the first point, correction to that of pressure, how pressure is corrected. VanderWaal's suggested to add some quantity to the pressure in order to get the ideal pressure. What he done? From the kinetic theory of gases, we know that the cause of pressure exerted by the gas is due to the continuous bombardment or collisions of molecules of the gas on the container in which gas is placed. Due to that, the force of attraction exerted on a single molecule striking on the wall that depends upon the number of molecules per unit volume in the bulk of that of gas. In other words, we can say the force of attraction is directly proportional to the square of density of the gas. Square of density of the gas. That is, the force of attraction is directly proportional to the square of density of the gas. The force of attraction is due to that of pressure, that is pressure is the force by area. As you take the number of molecules per unit volume in that of bulk is bombarded to the wall of that of container. So, pressure P is directly proportional to the square of density, let density be the rho. As we know, density is directly proportional to volume. That is why we can say P is directly proportional to 1 by V square. As we know, density is directly proportional to the volume. That is why in place of rho I substitute the volume. Now, we introduce the proportionality constant A. P is equal to A by V square. P is equal to A by V square, where A is the constant that depend upon the nature of the gas. A constant depend upon the nature of gas. This is the correction in volume, that is V minus B, due to the finite size of molecules, that is the correction in volume, and that is the correction in pressure, as the force of attraction is directly proportional to the square of the density of the gas, that is the correction in pressure. Now, by taking these two corrections, we can write the VanderWaal's equation for 1 mole of real gas. Therefore, for 1 mole of real gas, the VanderWaal's equation of state, that is correction in pressure as P plus A by V square, and correction in volume, that is V minus B, is equal to RT. So, the VanderWaal's equation of state, that is P plus A by V square whole into V minus B is equal to RT. That is the VanderWaal's equation of state for real gases, as you take 1 mole of real gas. Now, we have to take the comparison of that VanderWaal's equation of state for real gases with the experimental curve for PV diagrams. as we studied Andrews experiments on carbon dioxide. So here first from VanderWaal's equation of state for real gases, we know from VanderWaal's equation of state for real gas, that is P plus A by V square whole into V minus B is equal to RT. Expanding the bracket terms, that is PV minus PB plus A by V minus AB by V square minus RT is equal to 0. Now multiplying V square and then dividing by P. Now multiplying by V square and dividing by P, we get, that is VQ minus B plus RT by P whole into V square plus A by P into V minus AB by P is equal to 0. Look at that equation. Here VQ, V square, V, that is this one. This equation is a cubic equation in the variable V. As that is the cubic equation of variable V, hence for any value of pressure and temperature there should be 3 values of the volume V. Therefore, for any one value of pressure P and temperature T, there should be 3 values of volume V. There should be 3 values of volume V. Means out of 3 values, one value for volume will be real and other 2 are imaginary. So out of the 3 values, one value for volume will be real, one value for volume will be real and other 2 are imaginary. Okay. Now if we plot a graph for volume V against pressure P at constant temperature, then we found out the result. If we draw the graph, between volume V in x direction and pressure P in y direction at constant temperature, then the graphs looks like this. Here we get the points. C double dash, C dash, point B dash, B, that is the point A. Here the point as G, B dash, G, G dash. Here the point as F and that point the X. This is the dogma. This is the dogma. That curve at temperature 13.1 degree Celsius, that is at temperature 21.5 degree Celsius or 21.8 degree Celsius, that is the critical isotherm. Here we get the critical point as 31.1 degree Celsius. These are the curves as we find out from that of experiment. From the figure, it can be noted that for a single value of pressure, here for the single value of pressure, we get 3 values of volume. Look at that. This in the same volume segment. A single value of pressure, we get 3 values here, 3 values of volumes. The volumes are marked as C, C dash and B. Here we take the different volumes, here, here and here. When the temperature is kept as constant and which is equal to 13.1 degree Celsius. With the increase of temperature up to 21.8 degree Celsius, the isotherm moves up. The isotherms moves to that, and the 3 values of volume get closer as shown in the figure as G, G dash and F. These 3 values of volume are very close. Here be the volume. At a certain temperature, let we say 31.1 degree Celsius, the 3 values of volume becomes identical as shown in that of point X in that of figure. At a particular pressure, we get 1 value of volume here, means all 3 values of volumes are identical at that point at C, which is the critical point. At more higher temperatures, as we proceed like this, at more higher temperature, what happen? At more higher temperatures, the isotherms curves shown as this and that like this will depict only one real value of volume. Here only one real value of volume for corresponding to given pressure. Hence, from that of figure, we conclude that below the critical temperature of the gas, Here is the critical point and the temperature is known as the critical temperature. Below that critical temperature of the gas, the isotherm indicates 3 values of volume. Here the isotherms indicate 3 values of volume, and above the critical temperature of gas it will show only 1 value of volume for a given pressure. So we noted that one, that point from that of particular graph what we studied. The critical temperature, below the critical temperature, below the critical temperature of the gas, the isotherm indicates, the isotherm indicates, the isotherm indicates 3 values of volume, 3 values of volume, and above the critical temperature of the gas, and above the critical temperature of gas, critical temperature of gas, it will show only 1 value of volume, it will show 1 value of volume for a given pressure, for a given pressure, as we studied from that of particular graph. In the VanderWaal's experiments on carbon dioxide, as we draw the same graph between pressure and volume, we get the horizontal lines, but here the horizontal lines are absent, means it does not agree with the experimental isotherms for that carbon dioxide gas is obtained. So here we conclude that, again finally we conclusion, it does not agree with the experimental results, experimental results, as that experiments was done by VanderWaal's experiments on carbon dioxide. So here the portion B dash explains the supercooling of vapors, that portion indicates the supercooling of vapors, and the portion C dash, that portion is due to the superheating of liquid, that portion is the supercooling of vapor and that portion is the superheating of liquid. But we can't explain the portion C double dash, C dash and B dash, that portion cannot be explained in the isotherm, as in this portion of the graph the volume decreases, in that particular section the volume decreases with the decrease of pressure, with the decrease of pressure, but which is practically impossible. That is why at higher temperatures both the theoretical and the practical pressure volume curves are very similar. At higher temperatures the theoretical and experimental results of pressure volume graphs are identical, but here as we shown in that of VanderWaal's equation of state taking pressure and volume, which is not agree with the experimental results, as the experimental results was drawn by VanderWaal's experiment on carbon dioxide at various temperatures. So with the help of this video lecture we understand what is VanderWaal's equation of state for real gases, there will be two corrections in pressure and corrections in volume, and finally we derive the VanderWaal's equation of real gases and a comparison with the experimental curves of PV diagrams. Here we take the mathematical result as that volume, this equation is the cubic one. So, there will be 3 values of volume for particular pressure and temperature. That is why for these 3 values, one is real and another 2 are imaginary. By taking this, we take the graph of pressure and volume. So, that graph, comparing that graph to the Andrews experiment carbon dioxide for critical temperature, the gas is very similar, and throughout the type of gas we conclude that below the critical temperature the gases have 3 separate volumes at particular pressure, but above that of critical temperature the gases have one volume at corresponding pressure, and finally we conclude that it does not agree with the experimental results. So, with this useful and informative notes, let me wind up this session. Thank you.